Hi, my name's Jennifer Griffith, and I work at NMOA, which is the Northeast Waste Management Officials Association. We're an interstate association of the 6 New England states, New York and New Jersey, so the 8 Northeast states, the solid waste programs, the hazardous waste programs, the toxic use reduction and pollution prevention programs in those states, and also the waste site cleanup programs. And one of the main priorities for the wayside cleanup programs through NMOA is training. So that's what we're doing here today. So Mike, can you see the NMOA website on your screen?
Yep.
Yes, okay. So I just wanted to let everybody know that you can find out more about NMOA at nmoa.org, but also, let's see if I can figure out how to navigate here because of all these go-to webinars, also things getting in the way. Where people can find after this webinar later this week or next week, we'll be posting the PDFs of the presentations. And so I'll just let you know, and we're doing other webinars in the future in this series on PFAS, as well as already some are in the past. So I want to let everybody know kind of where you can find the stuff. So if we click on events, the website is, everything's slow. Uh-oh, my connection's not good. Okay, so basically the events are very forward focused. And so the ones that are coming up, so here's today's webinar, as well as the ones that are coming up in the future on PFAS, including, this is all events that NMOA is doing. So here's one that's more of a solid waste related one. But anyway, but if you click, you really got to know this little secret here. You got to click on this back arrow, and then you can find past events. I apologize for how slow my thing is going. So, and it starts, the most recent past is down at the bottom. So here's 2 webinars or 3 webinars that we've done recently on PFAS last week, 2 emerging issues, and then we did PFAS basics at August 7th. So you can find the presentations for those. And then today's webinar will also be in this past area after today. But I'll just click on this and you can see what it looks like. So, there's a little disclaimer, and then here you can click on these links to get the slides. So I think that's enough from me about what NMOA is. Like I said, the presentations will be posted. I'm going to change the presenter over to Mike and start introducing him in a sec. There's too many people on the webinar today for people to be able to ask questions themselves. So you can type them in at any point. I'll be monitoring the questions. So type them in at any point that works for you. You don't need to wait. And then we'll be doing questions after each presentation. Also new for NMOA is getting continuing education credits for Massachusetts licensed site professionals, so Massachusetts LSPs. So if you want continuing education credits because you are a Massachusetts licensed site professional, there's a few things that you need to do for sure. You need to stay on the webinar till the end. You need to not do other stuff on your computer. So I don't know if everybody knows or not, but GoToWebinar can tell if you're doing something else on your computer and this webinar is not like your top layer in the computer. So you really have to mostly the whole time of the webinar keep this as the top layer. You can't be checking emails and doing that kind of stuff if you want the LSP credits. I mean, other people should not do that as well, but also we're going to have to do some poll questions during the webinar just to verify that people are still attending. They didn't just put it on and walk away. So I apologize to others about that, but we are going to have to break for a few polls that everybody that wants LSP credits does need to make sure you answer each poll. And at some point during the webinar, you should also type in one question for the presenters, hopefully something relevant and, not too basic. And then even more importantly, after the webinar, you need to contact me and let me know that you do want an LSP certificate, because I otherwise don't know. So I need to know that. Let's see. Real quick, a reminder again, presentations from this webinar will be posted, and to type in your questions at any point during the webinar. With that, I'm now going to introduce our first presenter, Mike Eberle. He is he's a technical director at TRC Companies, and he's also a member of TRC's Centers of Research and Expertise, their core program. He is their PFAS initiative leader and their chemistry director. He has over 35 years of environmental consulting experience, including over 30 years of experience designing, troubleshooting, and managing the operation of multi-phase hydrocarbon product extraction, bioventing, and in situ and ex situ groundwater remediation systems. So yeah, he's definitely TRC's subject expert on the investigation and remediation of emerging contaminants, of which PFAS is certainly one, and also 1,4-dioxane. And with that, I think we just say he knows a lot, and he's going to share it with us today. So thank you, Mike. I'm going to turn my camera off and mute myself and take it away.
Okay. Is the presentation up there?
Oh, no,
Hello?
It's there. I see it. Yep, go ahead.
Okay.
You're good.
Get rid of this stuff.
Yeah, just click on the screen, and then the back and forth should work.
Okay. Okay, so the unfortunate thing about PFAS forensics and any type of forensics when you're making a presentation is you're limited to how much information you can actually show. So unfortunately, I can't show a whole lot of basically plan view site maps because of the issue with the forensics. And in most cases, all cases actually, all the data I present is public data, but my evaluation of it is not public. So I have to limit some of the information I can show. And I'm sorry for some of the confusion, but it's the nature of the information that I can actually present. In addition, it's okay. I'm gonna get on with this.
Yep, there you go. It advanced. You're good. Thanks.
Okay, so basically, I'm looking at some of the effects on forensics and source identification from the forensic evaluation, and that's what we're going to discuss today. So initially, I'll talk about some basic PFAS forensics and basic patterns across the board for a variety of different sources, and then issues that can affect the evaluation of forensic data or any data in a forensic way. Sampling is a big one. Differential fate and transport rates, how different compounds migrate through soil or groundwater, how they also the properties when they're at high concentrations and in source areas is also very critical to understand. And then the PFAS parent transformation, as we all know, PFAS transform the telomeres or the second generation PFAS compounds are basically telomeres, and they transform in the environment to other compounds, which makes it a little bit more complex. And then I'll talk about PFAS PFOS isomers and the fate and trans and forensics of those isomers. Initially, when PFAS first came out and we saw how stable it was, and we knew there were isomers associated with different lots when they were manufacturing PFAS or PFOA, we thought it would be a really ideal type of a situation from forensics information, but it's turning out to be a little bit weaker. Just because of the substantial different fate and transport properties of the different isomers. And then a case study with the fate and trans of a multiple release HFOF site, which most other sites are for airports or for firehouses or training areas. It's a lot of multiple releases over different times and different types of HFOF. And then I'll finish up with a brief discussion of PFAS mass versus PFAS concentration when you're looking at surface waters, and it's specifically the fate and trans of the forensics of surface waters. Up here's just a picture. I'm going fishing soon, so let everybody see a nice picture of the beach and surf fishing, so cell phones don't make it their way to the beach. Okay, just a simple example of how we look at pie charts and forensics from a pie chart perspective and how we analyze the data. We're looking at initially, let me see here. Sorry. Get a pointer out. How we look at the pie charts is the sulfonates are on one side in a group from shorter chain to longer chain. And this is essentially the first compounds that were manufactured, or the largest mass of PFAS compounds that were manufactured were sulfonates. So it's also a little bit of a history that goes along with it from short chain to long chain, more soluble or less soluble. And then the second generation telomere-based foams, which basically replace the sulfonates, come next, 6,2 and 8,2. There's others, but these are the major compounds that we identify. And then all the shorter chain compounds that were manufactured for the various different types of solvent issues and surfactant issues, but they're also breakdown products of the 8,2,6,2 telomers. So there's a little bit of a rhyme, the reason to it, so you can take a look at what's going on and get a real fast idea of what you're looking at. Just a huge group of different fingerprints. You can see that these are C6 normal fingerprints, a lot of AFFF, plastics manufacturing, but it's just an example of the variety of different sources. And I'm pointing out one thing here because it's really critical if you have a situation where you have a really unusual mix, and in this case, sulfonate, C7 sulfonate is the major component at this site, and that is a major different situation for this type of AFFF. It's very unusual, but whenever you see something like that, it's critical to identify that, and it's important because it's going to be easy for you to separate plumes when you have something unique. Another example, a little bit of blown up of different forensic patterns. Car detailing. Detailing is amazing source for a smaller business. But with car detailing, one of the sources they use are an alkaline, a strong alkaline surfactant, and it cleans plastic, cleans rubber and leather very well. But the issue with it is the surfactant has to be a very strong surfactant, or a very strong. It won't break down basically under the very alkaline conditions, and that turns out to be PFAS is one of the greater surfactants under these conditions. So that's why we have very high concentrations in some car detailing products that are still available on the market today. Paper mill sludge, the amine compounds, the phosphamine compounds are particular in basically different sludges, and it breaks down to basically PFAS, and that's what the major problem is in the groundwater, or migrating away from the soil with PFAS in it. Now, plastic manufacturers, PFOA-based landfill groundwater, there's a lot of PFOA and carboxylic acids. They're more soluble and they're more prevalent in a lot of different materials that are disposed of in a landfill. Private septic systems, currently they're PFBS C4 rich, because that's the compound that has replaced PFAS and hexane sulfonate. So it's the one that's most common in household materials now, stain-resistant materials such as carpeting and clothing. So that's what shows up in current septic groundwater. And landfill leachate is again a hodgepodge of compounds. The leachate tends to be stronger and contain a lot higher concentrations of telomers, while those telomers break down to their parent compounds in landfill groundwater. The different types of fluorine-based PFAS-based AFFF. It's not just AFFF that follows this basic trend. It's all types of PFAS that we use for stain resistance, used for all the different reasons we use PFAS. They also follow this same trend that AFFF followed as we moved away from one compound that was found to be prevalent in the environment moving to something that's less toxic, moving to something that's less toxic. We did that across the board for a lot of the uses of AFFF. So this is, PFAS. So this is an example of the changing composition of PFAS compounds over time. So the initial AFFF is a PFOS-based product that had various mixtures of hexane sulfonate in it, and that may have just been a manufacturing situation, but that ratio becomes important, and I'll talk about it in a couple minutes. But it's basically the first generation is PFAS, or legacy-based foam. The second generation were the telomere-based foams. They were sold from the 70s to 2016, but they primarily became the primary AFFF PFAS compound in the early 2000s, when PFOS-based foams and sulfonate-based foams were phased out. So they were always around, but they were the major, and they maybe 80 or 90% of the PFAS generated after 2000. They contain mixtures of 6,2 and 8,2 and some other telomers, but they're the primary telomers that are in this material. They break down to PFCAs. I'll talk about that later. And longer chained 8,2 can break down to PFOA. So that's more of a concern, and I'll talk about that being an issue in a number of slides. That's probably would be my #1 concern from an environmental perspective down the road, as being a long-term source of PFOA. And then the modern fluorotelomere AFFF C6 compound that doesn't really contain any regulated compounds. In the Northeast, it does contain heptanoic acid, which is regulated, but it's a minor component of 6,2, of the breakdown of 6,2. So generally, it's a more environmentally friendly material, and it functions the same as the longer chain compounds. This is similar to how gasoline went along. We initially had leaded gasoline. We replaced lead with MTBE and less toxic things, and then MTBE was an issue. And then we replaced benzene in it, and we came down to gasoline with low benzene, no MTBE, no diethyl, no tetraethyl lead. And we're kind of following the same procedure here, where we're ending up with a C6 compound that is still not great for the environment, but it's also not real harmful. AFFF formulations again, which I just showed you, and these are some of the pie charts for it. First generation is a PFAS-rich, hexane sulfonate-rich mixture, and this is commonly see this. It sticks in the soil for decades. A second generation is one representation of second generation foams is a mixture of hexane sulfonate and telomers. And then this is basically this is just showing you what the clean C6 soluble portion is. It's again a little bit of heptanoic acid, but mostly unregulated compounds, or compounds that are regulated at normal levels, where they're up around the ppb level. And another second generation foam, a mixture of 6,2, 8,2, and all of its breakdown products. This is a surface water impacted by AFFF release. Then the other critical situation is, say, because this first generation foam lasts so long in the surface soils, in smear zones, everywhere it was released, it has an extended life of decades, and we're not really sure, because we see residuals at high concentrations of residuals after 30 and 40 years. So it just slowly attenuates from surface soil or smear zones. Initially, for the initial 20 years or so of PFAS manufacturing, PFAS was the major component, with minor components of the shorter chain hexane sulfonates. So for 20 years or so, this was the major thing, and you had a ratio of basically PFAS to hexane sulfonate of about 8:1. As time progressed, that ratio decreased as PFAS were being replaced with a less, with a shorter chain compound with less issues in the environment than PFAS does. And it's also this is basically what the trend is that we're seeing at airports. The older sources, we're seeing a higher range of PFAS to hexane sulfonate. When we get into more recent releases, 1966, it's 2.4. 1990, it's 4.2. But we're seeing this trend where this ratio decreases with time. The poll question?
Oh my goodness, I got too many things I have to try to open windows here. But yes, poll question. Launch it. Which PFAS indicates an AFFF source? So again, if you want the LSP credits, you must answer, and otherwise folks should answer just if they want to, because it's easy. You just click on one. And we'll just let a couple more people vote. Looks like I can't tell how you're voting, but I can just see the percentage of people that have voted. We're almost at 80%, so that's a good number. So I think I will close this poll, although people are still voting. And then Mike can just tell us which one is correct.
Oh, I didn't see the question. I think it's PFOS. I sent it to you yesterday, but I don't see the question.
Yeah. Although some
No,
people
PFOS.
also voted for PFOA because I guess that is a breakdown product of the telomeres, AFFF.
Correct, and that wouldn't be incorrect. Would not be an incorrect answer, although it's also not incorrect. And I forgot to mention this, that PFOA, and you can see it at some DoD facilities in the mid 60s, and this is also an important concept. In the mid 60s and up to maybe the early 70s, there were some AFFF formulations where PFOA was the primary PFAS compound. It was made for a very short time period, but I've seen it at DoD facilities and fire training areas, at DoD facilities for that real old fire training sites. Okay, we'll move on. These are AFFF. This is a common situation too, and it's something that I've seen over and over again, and a lot of people have asked questions about it. But they're AFFF samples collected from a hangar tank, basically a storage tank, that have partitioned into a dark portion and a light portion. I can't remember which one. I think the light portion's actually heavier than the dark portion. So the dark portion segregates to the upper portion of the tank, but they're essentially the same thing. And manufacturers will tell you it's no problem. It's nothing big about doing that. That's not an issue. But just so when you see that, it just has something to do with the AFFF that's not particular to the PFAS. It's particular to some of the other additives in AFFF, where you see some of this slight discoloration. But you can see here that they're basically the exact same material and they perform the same. This is just something real fast to let you know that it's not unusual to see that partitioning of light and dark in AFFF concentrate. And I'll go back. I have a lot of text on some of these slides, and I'm not going to go over all the text, but I'll make it available after the presentation. Okay, so just a little background on the chemistry and the properties of AFFF. I mean PFAS compounds in the environment. It's kind of critical to understand this because it impacts everything about PFAS. Basically, they're telomeres. You have a hydrophilic head that likes to be in the water, and a hydrophobic end, and oleophilic. It only wants to be in air. That's the critical portion of PFAS compounds that are unlike any other surfactant. So a single compound or groups of compounds end up starting out like this, and as the concentrations are low, they may hang out at the surface and redissolve. But as the concentration starts increasing, they start self-associating as sheets on water surfaces. It could be a drop of water, it could be soil moisture, it could be a surface in a lake or a pond, or a static surface even in a well. And any disruption to that or increase in concentrations will tend to start forming bubbles, and they're called micelles or little bubbles. But they can become trapped everywhere. And it's not like absorbing directly to it as much as just being physically trapped inside the soil structure. And that's what the next picture shows, is that you have these various micelles and larger, like molecular aggregates and larger molecules, basically, or groups of molecules that actually become stuck in the different pore spacings, micropores or mesopores in sand or silt. And then electrostatical groupings of different compounds, I mean, of the PFAS compounds when they're in larger molecules or molecule aggregates. But they're there in a fairly stable situation if they're not disturbed. If you disturb it, either by mixing the soil up, by doing an SPLP analysis on it, by installing a well, you release a lot of these compounds temporarily, and you may pick them up and show a very positive bias, high concentration of compounds and larger molecular aggregates, such as micelles, bubbles, hemimicelles, whatever it may be, that are not mobile in the groundwater, and in many cases aren't mobile in surface water, and are just trapped in the soil, and it can slowly break down to individual molecules like this little tadpole here, and then be released into the environment. But it's a fairly slow process, and that's why we see some of these sources lasting for decades. It's just these molecules and these macromolecules jammed in the pore space. So we have the issue with just sampling the solids and how that may result in a biased high sample due to disruption of the environment. But we also have issues with the labs, and they're trying to work this out now, where some labs will analyze the solids, some labs won't analyze the solids. So that ends up with very inconsistent results that can affect forensics. It basically affects everything, which I'll show you a whole bunch of data for. So the best way to deal with this, certainly from a groundwater standpoint, is install wells, develop wells, and sample wells so you have very, very low turbidity. That's the easiest way to get representative data. And it's worthwhile replacing wells, making sure wells are installed correctly, and it's certainly worthwhile developing them. And then here's some of the examples for it. How much everything changes from this one site or one area based on a handful of wells. It all had this similar trend. Initial temporary well samples had a high turbidity. They weren't really developed, but it was a grab sample. Concentrations were high in 1,000 total nanograms per liter. In this case, it was hexane sulfonate rich AFFF source. And we had a bunch of compounds, PFOA namely one of them, well above any type of MCLs. A new well, was installed, a permanent well was installed, but the well was poorly developed and it was sampled still with residual turbidity. So we still have disruption of the smear zone where those macromolecules were, and we end up with a relatively high result, but lower than the grab sample. And you can see the regulated compounds are starting to drop down in concentration. Same area again. We have the 2-inch developed well, which I just showed you that information, 25 NTU. But then to continue this remedial investigation, it was required that grab samples and groundwater samples the wells be developed and purged to the point where you get the turbidity down as low as possible, hopefully below 2 NTU and certainly below 10 NTU. When that occurred, the concentration in the water at the same exact locations dropped down very low concentrations. And you can see if all these pies, whenever you see something like this, where all the pies or all the concentrations are very similar, that's almost, they may not even be there at all. And it just could be a laboratory issue with a whole bunch of estimated values or background type condition. But it's much lower, and this is more representative of what's actually moving in the groundwater. So I think what we're going to see in this case, it's a smaller release, and how we verified this, took a downgradient groundwater sample, and it was actually lower than this. It was almost non-detect. We're going to see a lot of cases where you have small AFFF releases or small PFAS releases where this is attenuation. It's not dissolving fast enough from the source smear zone to create a plume. And it's not just AFFF that we're seeing this situation with. It's other high concentration source areas. It's important to consider that this turbidity issue is associated with source areas, and most pronounced in source areas where you had a release, you had the PFAS basically raining down through the radiozone and then re-collecting in the basically smear zone and forming those macromolecules at the smear zone. So they rain down as individual or small groups of molecules, and they re-accumulate as macromolecules in the groundwater table. And I have a cross section to show that. But in this case, very high turbidity, high concentrations on the initial sample, again above 1,000 parts per trillion. Another hint, you see some high concentrations of less soluble compounds. So there's something wrong and there's something associated with solids here. You're above drinking water standards. A replacement well was installed here, and it was basically a double screened well, a double cased well in to prevent any type of trickling down of the well, and the well was purged to 18 NTU. Oh no, I'm sorry, this wasn't double cased. This is just a purging of this well. It was purged to 18 NTU, and the concentrations went way down. PFO was below MCLs, but this is more representative of what's actually in the groundwater at this location than the disturbed aquifer. So again, it's critical to purge your wells and develop your wells and install your wells correctly. Real fast example of how variable sampling procedures can affect everything about a sampling round. These were all the same wells sampled in 2 different rounds, 1 year apart. This is a round collected with a baler. This is done in very early in the PFAS days. People weren't aware of balers and the other situations in purging or anything. But this is basically the snapshot under a purging condition. This is the same wells with a snapshot under low flow, but no turbidity criteria. It's almost completely different. You would think it was a different site and different sources, and it just has to do with your sampling procedures. So sampling procedures not only have to be solid, but they have to be very, basically keep your same sampling procedures and don't, minimal changes to anything that you're doing from a PFAS sampling perspective. Again, here's another indication of what disruption of the soil does. And I talked that briefly before, but here's a typical solvent extraction of a soil sample. This is a fire training area that's been surface soil that's been exposed to elements for greater than 20 years. You can see PFAS is there. Even one of its parent compounds, PFOS is still present. That converts fairly readily to PFAS. But extracted with a solvent extraction, there's about 31 micrograms of PFAS in 100 grams of soil. The water extraction with an SPLP analysis removed 10 micrograms of PFAS. So 30% of the total PFAS was recovered in a SPLP analysis. Now we know that SPL now is not representative, even close to being representative of natural leaching conditions, because this soil sample has been sitting there for probably closer to 30 years, and it's still at a relatively high concentration. If 30% was removed every time you flush water through it, obviously the source would have been gone a long time ago. So SPLP is not real representative of leaching conditions, and it basically has to do with breaking up the soil and disturbing the soil, where you have an undisturbed situation. With the surface soil, the PFAS remains intact for decades. If you mix it up for SPLP analysis and blend it with water, you free up all of those trapped macromolecules and your concentrations, and you artificially remove a lot more PFAS than normal leaching, natural leaching situations. Okay, so I'm going to, we've already talked about this: transformation, retention of PFAS in soil, chemical to absorption and basically sticking of larger compounds, PFAS persistence, commix and commingling. We'll look at a little bit of PFAS or transformation. We've been talking about a little bit. Here's a pre-top assay of an AFFF water mixture. So it's basically a foam and water mixture. After the top assay, which oxidizes all the compounds that are in the foam, the concentration increases by an order of magnitude. That's all the parent compounds associated with the telomers, 6,2-FTSR basically, and then all the breakdown products. One thing that's critical, and I'll show you again with the top assay with the more natural conditions, is a lot more PFBA. C4 is generated under these strong oxidizing conditions. Basically, when I'm talking about parent compounds that aren't detected in AFFF, and a lot of PFAS materials, the same stuff that is used for again, it's not just AFFF, it's used in water resistant, stain resistant materials are not actually what we analyze for, but these parent compounds, which are very insoluble. and the nitrate and amine compounds with these big functional groups attached to the more persistent telomere, the A2 or 6-2. These are readily broken down in aerobic conditions in the environment and result in the 6-2 or A2 that we analyze in the lab. So it's not that big of an issue, except that you have to realize that in many source areas, the actual source is much higher than what the reported laboratory numbers are, because you don't see these parent compounds. The breakdown of the parent compounds, here's a PFAS tail. Here's this functional amine amide functional group I just discussed. And it breaks off right here under any aerobic conditions, aqueous aerobic conditions, usually in a relatively short time when it's a saturated aerobic condition. Half-lives can be anywhere from days to years, depending on the specific condition. Now here's a transformation. Again, a top assay, that's that light foam that I talked about before, that we see the same situation here. That's a 6-2, 8-2, and this is actually from the concentrate. We see the complete transformation of it, and again, a huge increase in concentration. In this case, it's by 30 times an increase in concentration. So 30 times the parent compounds were there at a higher concentration than the regulated compounds or detectable compounds. Again, we see a lot of PFBA, and it's an indication of the real strong oxidation conditions. Now we see this happens in the laboratory with these top assays. This is an example I just showed you on the last slide, where you have the complete transformation of the telomeres. But we're also seeing the same situation, just at a slower rate, in groundwater and aerobic conditions, where you see, in this case, this was groundwater below a more recent telomere-based second generation release, where the groundwater below the release is rich in 6-2, which is one of the primary components of the release to AFFF. And then just a couple hundred feet, not even that, maybe 100 feet down gradient, and over the course of less than a year, you have almost a complete transformation of the 6-2 to its daughter PFCA compounds. Now, completely different from the top assay, you see a much lower concentration of PFBA. And that we're seeing that everywhere, where the top assay sees it. So we got to be careful if we use the top assay to evaluate or to use it for any type of forensic evaluation, because of this serious issue where the top A is so strong it actually breaks the molecule apart some to form PFBA, while natural conditions form a much lower concentration of PFBA. Just a critical thing to understand, and helpful to understand the fate and transit PFAS. Same thing again, I'll go through this really faster, but Lebegetic was a huge release of AFFF in Canada, where they used almost all the AFFF in the country to put the fire out. There's a huge amount of data on this. It's a great thing to review for the fate and transit of telomere-based foams. And the same thing I just showed you, we have the 6-2 and 8-2 transforming under aerobic conditions in groundwater naturally with a lower amount of PFBA. Okay, so then we're talking a little bit about branch chain. I talked about this in the initial kickoff, is that we thought that the isomer situation would be a way to identify different PFAS manufacturers, where isomers, the isomer mix of linear to branch chained isomers was associated with each batch of PFAS that was made, or PFOA. It's usually about 80% to 80 to 20% linear to 20 to 20% branched in the raw material. And it gets enriched by natural migration and solubilities. And so that's why it's less important from a forensic standpoint. But the surface soil at this one site, it was a firehouse. It is a firehouse. Was not even the surface soil is enriched in linear, the less mobile compound. And as you get down in depth, down to 32 feet, it becomes enriched, less enriched in the linear and more enriched in the branch. And that's just simply made because the branch chain are a little bit more soluble and can move a little bit faster through the soil column with precipitation. So it changes the forensic profile, it changes the mixtures, so it's not really that great from a forensic standpoint, but it's really good to understand the fate and transport and tie deeper sources and groundwater sources back to shallow sources. We have a similar situation here where I'll just talk about this one, and you can review this other ones. I'm running a little bit late here, but where you have a PFAS hexane sulfonate mix. In the shallow soil, you don't see a whole lot. The orange here is hexane sulfonate. You don't see a whole lot in the soil of hexane sulfonate. It tends to be more soluble and flush out to deeper soils down around the groundwater table. But what is there, and what we're just learning right now over the last year or so, is the amide of hexane sulfonate. That was one of the primary components in AFFF that wasn't well documented, and that still is probably present in the soil. It's not real soluble, but it transformed to hexane sulfonate, and that's how it ends up accumulating in the groundwater. We have a lot of sources where we see hexane sulfonate in the groundwater, but not in the soil, and this may be the reason. Okay, so and then here's another one with the stability of second generation foams, or anything you may see at a fire training area. We have first and second generation foams. Surface soil that's not protected this is similar to what I showed you before, where you have PFAS rich, A2 is richer in the deeper soil, and then you have a less A2 in the down towards the groundwater, because it's just not that mobile and doesn't degrade that fast. Now, under anaerobic conditions, underneath this cap, basically, this soil sample was collected underneath an asphalt cap, or just asphalt. It wasn't really cap, it just happened to be covered, this portion of the fire training area. You can see 6.2 FDS still in the surface soil. There's no degradation at all, and there's nothing transformed down into the deeper portions of the soil. This is just a cap that just happened to be there. They put a asphalt parking lot over top of a portion of this area. It shows the effectiveness of caps, and this is a repeating story I'm seeing over and over again. Even caps, just landfill, just parking lots that just happen to be installed above a fire training area, are very effective at containing residual PFAS in soils. Again, we see a similar situation. This is the PFAS migrating down gradient. We see the breakdown of the telomers to the more soluble components, and the soluble components moving a lot faster, 6.2 included, than PFAS or hexane sulfonate.
Mike, this is Jennifer.
Yeah.
We're starting to run out of time. We don't want to shortchange Matt, and we do have a bunch of questions. So hopefully you can wrap this up in
Okay,
another
I can end it here. This basically sums up this section.
Okay. Yeah, so obviously Mike has a tremendous amount of information and knowledge, and these slides will be very helpful to people, I think. So we have a bunch of questions about the turbidity issue. So, but before that, I'll ask this other one. Are there changes in environmental conditions that can pop those micelles? So can it happen naturally, or it's just when you're in there investigating and remediating?
It was the first situation I looked at from areas where you had moister soil or drier soil, or you had climatic changes that went from dry to moist. And it looks like there's a little bit of, it's a little bit less stable when you have very high swings in soil moisture, from going to bone dry to saturated conditions. That tends to free up the PFAS a little bit more. I don't know of a study on it, because it's really a long-term thing you're trying to pick up on, but I think there is a little bit of an increase in migration rates when you have huge moisture swings in the soil. It's definitely obvious in surface soil and surface water when you have saturated conditions and rain on top of saturated conditions. You tend to see a lot more PFAS migrate from a surface water perspective.
Okay, so about the turbidity. So there are several of them, but I'll ask this one first. So if the turbidity and the fact that if you really develop the well and get it real clear, then you don't really have much PFAS in the water, that doesn't seem accurate, because why do we have large PFAS plumes? Are you suggesting that soil particles are migrating in the aquifer? How,
Oh no.
Yeah.
No,
So
no, there are normal PFAS plumes. I picked the examples I gave you were examples where sampling impacted the investigation and remedial investigation and planning based on biased samples. if you have a fire training area or a substantial release of AFFF or a large jet plane or whatever it may be, you definitely have PFAS plumes. Where you have that concentration of PFAS in the smear zone. This is an example of what I'm discussing here, basically. But if you have this large source here, this is a condition where this is a fire training area for a couple events where you had maybe anywhere between 500 or 600 gallons of AFFF released or foam released. A 500 or 600 gallon concentrate, so that's 10 times or 10,000, 20,000 gallons or more of foam. You tend to form a smear zone here with the micelles trapped in the soil moisture of the A-horizon soil, and then you have it accumulate again as it rains down through precipitation and infiltration. You have the soluble components rain down through the vadose zone, and they reaccumulate in the groundwater and form a smear zone. If that smear zone has a high enough concentration of PFAS, it ends up in a pretty substantial groundwater plume. That's what we see here, a huge amount of this second generation foam. Yet at the same exact location, or very close to it, you had a first generation release in the early 90s, but it was only about maybe 3 or 4 gallons of concentrate. So 30 or 40 gallons of foam were vapor suppressant, which is also then excavated with the avgas, so it's even a smaller mass. You see that raining down and accumulating in the groundwater or in the smear zone. And a turbid sample showed a pretty high concentration of PFOS. But the sample right below it with less than NTU shows no PFAS. So the mass of this release was too small to generate a plume, while the mass of this release is high enough and large enough to generate a plume. So you definitely have PFAS plumes that are soluble plumes. It just depends on how much mass is released and how unstable, I guess, the smear zone is.
Right. Okay. One last question, and then we're going to have to switch it over, and then we can go back to other questions at the end if we have time, or people can stay a little bit longer after 3. But are you recommending that samples should be filtered so there aren't, so they're not turbid before they're analyzed? And what kind of analytical methods are used? Yeah. So how does that play into it?
Okay, we shouldn't be filtering samples because it's not clear whether or not we're going to be filtering out the mobile components of PFAS that aren't associated with the solids. In most cases, we probably won't, but nobody really knows for sure. So filtering is not the best idea. It's the best thing to do is to collect turbid-free samples, and if you have wells that can't be developed or wells that were poorly installed, it's best to replace them. Now, what we're looking at here, and one key thing to remember from a turbidity standpoint, is that this turbidity issue, and when you disrupt the stability of this smear zone, basically, where you have these micelles and larger macromolecules that can't move, you disrupt it with a well, it's a very local phenomenon. It just impacts your samples, basically. It doesn't release a plume. So the best way to get around it is install a well that you can clear up so you can remove all of the turbidity and disrupted water that's associated with just purely installing the well. And that is usually the easiest way to tell that is when the turbidity clears up. Downgradient plumes are basically more of a soluble PFAS where you don't have macromolecules. The turbidity is not as critical downgradient as it is in the source area. And there was a report that was just put out saying that turbidity isn't, there's not a huge correlation of turbidity and concentration. Well, the report didn't segregate the data from source areas to downgradient plumes. In all source areas, I'm seeing this biased high sampling result when you have turbid samples.
Okay, one last thing. One last thing before we switch now. Here's another key thing, I think. So what is the best way to determine leachability of PFAS from soil if SPLP is not the way to go? Or what do you think?
There's a huge amount of research going into that right now. And something that's less biased is actually collecting soil columns and reproducing nature on how often you have precipitation events. But unfortunately, that takes a long time, years and years and years. data. So one other one is that they're saturating soil columns, leaving them sit for a little while, and then letting water flush through them. And that will still be a biased high result because of the long-term saturation of the soil column with that extended saturation period of the soil column. But it's a little bit more accurate than SPLP. It's still biased high. There's a lot of research going on with this right now, so hopefully somebody will come up with a shorter term test and a less expensive test than collecting actually natural soil columns. But for now, natural soil columns are your most representative data.
All right, well, Mike, this was great. We could have had you present for an entire webinar, and maybe we'll try to have you back. But thank you so much for all this information. But we do need to switch it over now and have our next presentation. And like I said, if people can stay a little past 3, we can do some other questions towards the end. But I'm going to switch it over now to our other presenter, Matt Dunn. He's a chemical oceanographer at Tetra Tech. He focuses on the fate and transport of man-made contaminants in environmental waters. His work primarily focuses on PFAS. He primarily focused on PFAS during his academic studies at the University of Rhode Island in their Superfund Center there. But he's expanded to include other emerging contaminants and ocean carbon chemistry projects as well. And in addition to being a technical scientist, he works as a science communicator and a journalist. So with that, we do have a poll question real quick to do first.
You want me to take this down?
Nope, it'll pop up in over top. So just real quick, where does Matt Dunn work? Is he at CDM Smith, the US EPA, Tetra Tech, or TRC companies? So just vote. And again, if you want the LSP credits, you must vote. Other folks can. Let's just see if we can get it correct. It doesn't really matter. Just trying to verify people are here and paying attention. We could get a couple more people voting, but basically, let's let it jump up a tiny bit more and then I'll cut it off. Great. All right, I'm going to close it. The answer was Tetra Tech. Our previous presenter, Mike Eberle, he's at TRC companies, but most people voted for Tetra Tech, which is the correct answer. Okay, with that, take it away, Matt.
All right, and you can see my screen, right? Not the presenter?
Yes, I can see your screen in the correct mode. Yes, and I'm going to mute myself, and Mike should probably mute himself as well. Okay, thanks.
All right, thank you guys so much for listening to me speak today and giving me the opportunity to talk. I'm going to talk about forensics in relation to precursors, but also in relation to the way that we sample, the tools we use to sample, and the tools we apply for forensics. And a lot of this is stuff that is research from my PhD, but it's also stuff I'm developing now at Tetra Tech and RPS. So RPS is where I work. We were bought by Tetra Tech, so both answers to that are correct. And I work in our water division, so working on anything and everything that has to do with environmental water. So I won't belabor the background on PFAS, but as you know, there's so many different types of PFAS, right? There's thousands and thousands of these chemicals that exist. Everything from some of the new replacement precursors, studies show that they also bioaccumulate in different tissues. We know that, as Mike said, a lot of these precursors break down. They break down in the environment, they break down in the lab, they have different chemistries and different transformation. And part of that issue is that, you know, this great study from a colleague of mine, Bridger Rule, where he showed that, you know, AFFF use could result in hundreds of years of contamination, even if we stop using AFFF right now, just because the stuff sticks around. It slowly transforms, it stays in the vadose zone, it stays in the water. And that's something we'll touch on a little bit in relation to forensics, because that's actually a big complicating factor, you know? And it kind of coins this term I use all the time, the fluorinated feedback loop, which is that, you know, PFAS get used because they're really good at their jobs, right, of making things waterproof, stain-proof, putting out fires, which means they reach the environment, they get used, they get out, they get in us, they get in our food, So then the industry shifts to a new precursor, but then that reaches the environment and the cycle kind of repeats, you know? So an example of that is things like the FTOHs, where you've got this non-polar compound that is hard to detect in water, right? Because it's non-polar, it's often volatilized, but it can turn into a long chain carboxylate. It can turn into a shorter chain carboxylate. It can turn into a different precursor that's relatively stable and toxic, or it can turn into PFOA, one of the, you know, wonderkins of the PFAS world, the flagship PFAS, so to speak. So you got a lot of different processes going on, and a lot of this can complicate your forensics, right? So when you're doing forensics, and this is going to be a more broad discussion and presentation on forensics, you know, it's really only as good as your data is. And I think you always have to ask yourself, what am I looking at? What kind of measurements do I have? Doesn't matter if it's sediments, surface water, air. What are the detection levels? What are the number of compounds you can detect above those levels? What method are you using? Is it an EPA method? Is it a different method, right? Do you know the sources, or are you looking for the sources? These are just all questions I think you need to ask yourself before you do forensics. And I don't think enough people ask themselves this question, because at the end of the day, a lot of forensics is done on grab samples, right? And grab samples are great, right? There's EPA methods for grab samples of water, sediment, fish tissue. Fish tissue is a good measure, but you know, grab samples of water and sediment, that only represents one time, one place, one set of conditions. That's not really a representative sample of what's going on, right? So that's where I always say, if you're going to do forensics, using things like passive samplers can really improve your forensics approach, because these passive samplers, and I have a bunch of them up on the screen, they provide you with things like time-weighted average concentrations. And so on the screen, you see different examples of passive samplers that have like extensively published literature. The one right here with the white tube on the string is the one I used for groundwater and surface water. And there's two kinds of passive samplers. So before we dive into forensics too much, I want to quickly go over the types of passive samplers, right? On one hand, you've got your equilibrium passive sampler. That works very simple. It reaches equilibrium with the environment, and you simply use the equilibrium coefficient to get your time-weighted average concentration, right, in the water, in the sediment, in the air. Those don't really work so great for a lot of PFAS because of their polarity. These are great for non-polar things, PAHs, PCBs, non-polar PFAS like FTOH. Typically for PFAS, we use something called integrated, which works for polar compounds like PFAS. And it uptakes a little bit more every day. And it uptakes PFAS based on their physiochemical parameters, which is why you need something called a sampling rate. It's not super important to remember that. I'm just trying to give you a little background to the difference, right? So here you're using an equilibrium coefficient to derive a concentration. Here you're using a uptake rate. And I want to show a couple of examples of why passive samplers are so great for forensic efforts, using two examples from my PhD. And, you know, while a lot of passive samplers, while there isn't an EPA method that's published for them, their EPA, state agencies, federal agencies use them. They love them. They may not use them in litigation, right? Because, you know, can't necessarily bring a passive sampler into the court of law without an EPA method, but doesn't mean you can't use it to do a better job of, you know, better scientific job, even if it's just not for permitting. But a lot of the work we do here isn't for permitting, it's for science. We're helping people figure out where their PFAS is coming from and what to do about it. So one example of this was how we used a passive sampler to do forensics on one small river in Rhode Island. And this is a schematic of that passive sampler before, right? It's a very small tube, 7 centimeters long, microporous, filled with a sorbent that's just like the sorbent you use for water extraction, solid phase extraction, and it's capped on both ends. And what we wanted to do is we went to this small river, an estuary, that had a bunch of different textile mills, some still active, some closed with these old waste lagoons full of PFAS, and they were all reaching the river in close proximity, but in very different ways. And we wanted to see, you know, if we use passive samplers, can we capture a little bit more of that environmental variability to distinguish the profiles and distinguish, you know, the sources, basically, you know, how do we tell which textile mill is contributing what? So like I said before, why passive sampling? Well, because we want a time average concentration. If you look at this fake line graph I have over here, if you took a grab sample here and did forensics and analysis, that would give you an incredibly different understanding of your system, of your data, of your field site than if you took a grab sample on this day. You know, this is Friday, this is Monday. That's what a lot of these dynamic systems are. You know, albeit groundwater might not be that dynamic, but river water, streams, oceans, coastal estuaries, and bays, these are very dynamic systems, and the concentrations fluctuate quite a bit based on the source. And so what the passive does is it gives you an average, something between this, which is just far more representative than a single grab sample. It's not that grab samples are bad, but it's that, you know, it's a limitation of using them, right? And this is a way to potentially get around that limitation. And the reason you want to get around that limitation is because you have all these different things that affect things like rivers, right? You've got, if it's really hot in the summer, the water level drops, you get concentration. Maybe you have discharge from wastewater treatment or from a factory. Maybe it's consistent, maybe it's not. Maybe it happens once a week, once a day. You know, in the Northeast where I work, we have a lot of hurricanes, which leads to a lot of flooding. So you may be mobilizing PFAS from sediment into the water, or you may be diluting the water, right? Because you've added all this water, fresh water that maybe doesn't have a lot of PFAS. So you need to understand why and how your environment's changing before you can focus on forensics, right? And for us in this textile-derived river, why we were really interested in forensics is because if you look at the river in this close-up picture, we had these waste lagoons running from the textile mills parallel to the river here. And they were technically closed off by a little board of wood, beautiful wood here as you can see, but the minute it rains, all that PFAS-loaded water runs into the river and you've got a source. And this is a common thing used around textile mills. The two I studied in Rhode Island are not the only two that use this. Currently, the US EPA says there's about 93 active textile mills in the US. They don't report closed ones through their TRI, but there's probably quite a bit of textile activity out there that's a source of PFAS. And textile is generally understudied, right? You know, Mike gave a great overview of all these different uses, AFFF, different AFFFs, plastics, but textile is a big one too, you know, and some of those textile mills use PFAS that have very distinct chemical and transport fingerprints, right, compared to AFFF. So that's what we wanted to experiment. And by using the passive sampler, right, we're able to get a little bit more representative data because we're taking that time-weighted average. And what we saw was that if we do something like a PCA, which is a simple first step principal component analysis, we got pretty good separation of the grab samples. You know, pretty good. You know, you start to see some of the grab samples separate out, but, you know, they kind of mix in. Up here, we see some of the active mills, we see some of the old mills. And this is pretty good resolution using both passive sampler data and grab sample data, right? You kind of get three distinct clusters. When you use just the passive sampler data and you do something like a k-means cluster analysis, which is just another strategy that people often use for forensics. I'm not going to go into, you know, great details on it, but it basically is a function that will tell you how many groups your data should be divided into based on their dissimilarity or similarity to each other. So you get a much more refined cluster than you do with something like a PCA. And specifically when we used the passive sampler data, we got really big separation where we had all the grab samples kind of separating out from all of the passive samples, which at first, I remember reviewers of this paper being like, wasn't that a bad thing? And I was like, no, if they were exactly the same, you wouldn't need to use a passive sampler. The point is, these are discrete, one time, one place measurements, and these are time-weighted averages in a dynamic system, so they should be different. And then over here, you still see the separation out of your waste lagoons. However, it's broken down into the two different kind of waste lagoons, right? So now we saw all of this specific factory, and this is a different factory with a few points that are kind of shared profiles from this one, but ultimately we could kind of distinguish the two factories using passive sampling. And I know I'm kind of going over this very broadly, but the point is just to show that, you know, when you have these time-weighted average concentrations, you have a much better idea of what you're looking at. We recommend using, you know, 2 weeks worth of data to a month's worth of data, and you're able to basically resolve things a little cleaner than you are with, like, say, a PCA, right? And one of the biggest issues you run into when you're doing statistical approaches like this, whether it's with passive samplers, whether it's with grab samples, is what do you do when you've got zeros or non-detects? In the past, you know, academics, like when I was doing my PhD, we've replaced non-detects with, or below detection limits with the method detection limit divided by the square root of 2. There's a lot of papers out on what to do, you know, because it's not really 0 per se, right? That's another issue with PFAS, is just because you can't detect something doesn't mean it's not necessarily there. Depends what your MDL is. So one of the advantages of using passive samplers is that you have the ability to measure PFAS over a longer time. So if you get something below detection limits, it's probably not there. While it might not be 0, it's a lot easier to say, well, it's probably not really there. It's probably not something we're worried about at this site. And the way that I learned to deal with this was, because I'm a chemical oceanographer, I took a lot of biological oceanography classes, and I looked at how do the people who study phytoplankton community compositions deal with statistics? How do they deal with forensics? How do they deal with trying to map out why, you know, March on the coast of the US is different composition of phytoplankton from April on the coast of the US? And they deal with things like zeros, or they deal with detection limits when they're doing genomic sequencing. And I learned a lot about things that they do, especially from this wonderful paper in limnology and oceanography, but they deal with things like zeros by using non-dimensional scale analysis, NMDS and RDAs. K-means clustering. But you can also learn from this to treat PFAS more like presence absence. If you have a lot of sites, you don't necessarily need to plug all those concentrations for each individual site into your statistical profile. One of the things I've really experimented with is presence absence. At this site, at this river, if you're comparing multiple rivers, how many sites did we sample? How many times did PFOA pop up? And this is one of the really creative ways you can move forward and kind of look at expanding PFAS forensics outside that intermediate or beginner level. Oh, I'm just going to run a PCA. Oh, I'm just going to run an NMDS. This is where you really we as a community also need to get creative, because PFAS have unique chemistry. They have unique breakdowns from precursors, and it's complex. So we got to just try a little bit and get a little creative. So for me, that's meant diving into biology. And the reason I dove into biology specifically is because you've got all these replacement compounds, right? And they highlight that, you know, they're not going to reach the river the same way. Even if the 2 textile mills are putting out the same PFAS, they may be releasing different PFAS that break down to the same endpoint. And that's why we wanted to use the passives to try to get a better understanding of that. And what we saw was that the passive samples were statistically or significantly different than the active sample results at each site on the river, right? So again, I remember one reviewer being really upset about this until I had to get into a little bit of a debate with them that no, that's exactly what we want to see. We picked a river that's dynamic, that's changing. Even the grab samples, the active samples in purple here, have massive error bars, massive standard deviation between the concentration, because it's changing all the time. So what we want to see with the passive sampler is maybe a more representative picture of what's actually there. And that's what we did. We wanted to do that to capture things like FTCAs, which break down from those FTOHs. We wanted to get a better understanding of whether it's potentially coming out of the sediment or the air. And now there's a part 2 to this project that hopefully we'll get to present on in the future, where we use passive samplers to try to differentiate sediment versus air results in the water. And it kind of underscores this complex path from industry, you know, to the water, whether it's a river, estuary, or ocean. That's really hard to capture via grab sampling, because as we heard in the last talk, you know, you have issues with turbidity, right? Well, passive samplers only sample the dissolved phase. So for some projects, that might be a limitation. For some projects, that might be an advantage. In this project, I filtered all the grab samples so that I could compare only the dissolved phases to the passive samplers. I also extracted a lot unfiltered so I could compare. And I actually have a publication coming out, hopefully, knock on wood, where I show the comparison of filtered versus unfiltered water samples, the same sample split in 2, and we see which types of PFAS are most affected by that. The spoiler is that some classes of PFAS show big differences, others don't. And that's another thing with the passive sampler that you can tease out. You put these in groundwater wells, you're only sampling that dissolved phase. It's super useful. And again, with passive samplers, another reason to use this for forensics, when you want to decide or determine the mass flow, right? So I think Mike mentioned in his last talk as well, you know, the difference between PFAS mass and PFAS concentration, right? And how you can use that in forensics to look at fluxes, to look at mass flows, to look at source export, you really want to use a passive sampler for that, because the passive sampler was deployed for the whole month of June. And we are able to use USGS data to get, the total discharge for the month of June, or the average discharge for the month of June, down a river, down an estuary. And what you end up with is a much more accurate estimation of the mass flowing down that river, right? Versus one grab sample. This has been super important to show. For example, we were able to show that the active mills upstream were not releasing nearly as much PFAS as the closed mills downstream. Waste lagoons here, meaning the waste lagoons from the old closed textile mills. And this was a really big finding, because these are not far from each other. I mean, these are miles or less. Even close, in some cases, they're less than a mile from each other. And we're able to really distinguish those mass flows and use that to sort of tease out on the river what's going on. And so we'll take a quick break for a poll question you can throw up. I also left it on the screen. And just let me know when everyone's answered, and I'll move on. I can't hear anyone, so if I'm just going to move on unless someone stops me otherwise.
I forgot I was muted.
No worries.
Oh my goodness. All right. Well, anyway, I closed the poll. Can you just say what the correct answer was and why?
Yeah, so the correct answer to this is no. If you go back to one of my early slides, we see that the FTOH starts out as a non-polar volatile PFAS, right? A neutral PFAS. It breaks down into charged PFAS, like PFNA, PFOA, which are polar, have a negative charge, are no longer volatile, would rather be in the water. So it's really important to look at that when you're considering forensics, because and passive sampling helps you sort of pick up those precursors during their transformation processes, because once the precursor dissolves into the passive sampler or diffuses into the passive sampler, it cannot transform once it's in there. So by having that out for a whole month, you're able to capture the different chemistries as they're transforming. So moving on, I talked a lot about detection limits and passive sampling, improving that. And I wanted to use an example that's not necessarily forensics based, but is a really good example of why passive sampling helps forensics, right? So we went out to the middle of the ocean, the middle of the Fram Strait, the north, where the Atlantic meets the Arctic, and we left these passive samplers for a whole year, as deep as 2,500 meters, sampling water that was everything from 0 to 250 years old, based on oceanographic principles. Now, this is a really hard place to sample, because a lot of people have done it before, but you get really low levels in the Arctic, right? You got really low levels. And in the past, a lot of these studies have shown that there's this recirculating pattern around the Fram Strait, where basically whatever is exported to the Arctic from the Atlantic, equal amounts are exported back to the Atlantic. Doesn't matter what pollutant you're talking about. They've done it with PAHs, PCBs. My study did it with PFAS. So this is really interesting, because it talks about, sure, maybe there's extra sources up near those Arctic communities, but it's kind of leaning into that idea of the fluorinated feedback loop, where, well, a lot of these PFAS don't really sink out when they go into the ocean. They can, in fact, come back around for a second go round near your coasts. And the reason that's so interesting is because, these are really low concentrations, and it's really hard to apply forensics when you're really far away from the source. We were only able to detect so many PFAS, and that was even with ultra low, detection limits, right? So up here in the Arctic, we were looking at picogram per liter levels of PFAS with the passive samplers, which is not something you can do with grab samples for the most part. Typically, a good grab sample, maybe your method detection limit is around 500 picograms per liter, right? And here we're able to find a whole slew of PFAS, from short chains to the legacy long chains, and even some fossa. And we were kind of trying to say, well, let's look at what that profile kind of looks like when you're really far away from the source. And what you see is a lot of those precursors dropped out, right? They've really been transformed, they've sunk out, whatever happened to them, they're no longer really in the picture. And this is super important because so now that we can go up there and we can measure the PFAS at really low levels and we can identify what's happening in the Arctic, we can identify that there's this feedback loop of export, right? What's going out or what's going in is coming back out. How do we, if we're doing coastal forensics, right? In estuaries, bays, open oceans right on the coast, how do we distinguish this recirculated PFAS from sources in coastal systems? Because if you're seeing PFOA, PFOS, PFHXA, some of that is moving around in the ocean and coming back up and down through, and that's really controlled by the hydrodynamics of the ocean. As an oceanographer, I could talk about that forever, but I won't bore you with it. But we've really got to focus on turning the tap off, because it's going to get harder and harder to apply some of these forensics approaches unless you expand your analyte list, right? We're going to see more and more sources that are both bringing PFOA, both bringing PFHXA, all three of them are bringing PFPEA. And we've got to find more ways to distinguish these sources using a greater list of compounds with lower detection limits. And that's really what we saw here. The passive sampler, the calculated method detection limit for a passive sampler is about 48 picograms per liter. That was on average. The PFOA for a solid phase extraction, the average for the solid phase extraction was not very far from PFOA. It's 840 picograms per liter, right? That's still good. It's sub 1 nanogram per liter, but especially with the really strict limits now for EPA regs for drinking water, we've got to do whatever we can to lower detection limits, find more compounds, find them at their different precursor stages, their different charges, transformation products, and use that to try to tease out where the PFAS is coming from. And the reason passives can do this is because it's like putting an SPE cartridge in the water. For those who don't know, the SPE cartridge is what we use to extract a PFAS sample, right? We take it, we run it through a cartridge, we elute the cartridge, we put it through LCMS. So the sorbent is the same thing that's in that, and we're just putting it in the water, and we're essentially extracting the ocean, extracting groundwater, extracting a river in the field. So we're sampling a huge amount of water, allowing for more and more and more PFAS to accumulate inside, thus lowering the detection limits. Because if you extract a grab sample, you can only extract so much. You might only sample a liter of water, right? It's very laborious, it's very time consuming, it's very expensive to extract water. I've done it hundreds of times. This is a lot easier, these samplers are renewable or reusable. And the point is that with more detections, whether that's more detections below the method detection limit, right? So you're able to find more compounds because your MDL is smaller, or whether you're just finding more compounds that you might not get with an SPE analysis, we've now got that improved capability for statistical approach. And that's what we were able to apply up there and see that we could actually separate out PFAS profiles based on what water mass we were looking at, right? So we saw the biggest discrepancies between the really deep water that's hundreds of years old, where the only PFAS comes from stuff that sank down, versus the polar water. This is what was heading into the poles, or heading out of the Arctic, I should say, back into the ocean. That had a really different profile than the Atlantic water that was generally heading in. So that shows us right off the bat, this might still have some precursors, or it might still have some, different sources, right? Because it's coming from Europe, the US, where there's active PFAS use. And whatever's sticking around is what's getting exported. And you can see that when you use good environmental data for your forensics, we were able to put these on buoys at depth with salinity, temperature, velocity, all other things. But you can use DOC, you can use TSS, you can use different timescales. You can really, really help improve forensic resolution. And that's true for grab samples as well. Even if you're not convinced that passive samplers are the future. And listen, I don't sell passive samplers, so I don't get any money if you believe me or not. But even with grab samples, take as much environmental data as you can. What's the salinity? What's the temperature? Did it rain? Did it rain yesterday? Is it going to rain tomorrow? What's the base flow? These are the things that are really going to help separate out forensics approaches. And that's one other thing I learned very much from leaning into the biological oceanography community. It's super important to use what you have as a scientist to make better decisions. All right, don't just measure the 6 PFAS that EPA tells you to measure and think that you can necessarily do great forensics, because it's not necessarily going to work out in your favor. So I'll wrap up here in a minute, but I just wanted to say, like, things like passive samplers and things like models. I work on a lot of modeling here at Tetra Tech and RPS. These are just tools. They're not necessarily replacements for grab sampling. They're things to do with it. These are tools in your tool chest to figure things out. You know, I've just told you about passive samplers, which is what my research was on, but I also suggest you use things like numerical models, Lagrangian models, Eulerian models. The one I work with is called ChemMap, where we're looking at using environmental data, currents, wind, tides, and the chemical parameters of PFAS to see where they go from a source, right? We can use historical environmental data. We can project forward. It's called forecasting or hindcasting, and use this stuff to your advantage. It's not necessarily better. It's not necessarily going to give you an answer, but the more things you lay out in front of yourself, the better the answer is going to be, right? So the more you can say, oh yeah, the current is telling us that the plume is going to move this way, the more you can begin to think about where you should sample. Is that even reasonable that you saw PFAS over there? Is the, you know, the source is only releasing PFOA, but over here we found PFOS, so that's clearly from something else. And you can get information on the mass balance. How much is going to go in the water column? How much is going to bind to sediment? And these are all important things to think about. Is the sediment going to be a source or a sink? In this specific test case I was running, we found that the sediment was the source. PFAS was released near the bottom, bound into the sediment, and as the sediment was transported away, it diffused off when that gradient changed between the water and the particle. So you mobilized sediment, it shot it into the water. So these are just tools. These are, like I said, they're just tools to create these sort of paired approaches where you do really comprehensive site evaluation using passive samplers, using stats, using models. And, you know, like I said, forensics should always be based on fate and transport. It's got to pass the eye test. And that's, you know, that's the thing. If you expect to see something at the surface micro layer and you don't see it, dig a little deeper. If you expect to see something in the sediment, you don't see it, dig a little deeper, because that's what we do every day. It's got to pass the eye test. It can't just be stats. It can't just be models. You've also got to think about it. So I think that's it for me. Yeah, I'll call it there and wrap up.
Great. Well, we do have a bunch of questions, so thank you again, Matt. So how about using passive samplers for groundwater, not just surface waters?
Yeah, I use them for groundwater all the time. I use it for groundwater near military bases. I have published research on sampling in groundwater, and it works great as well.
Okay, and how about just what type of media and you know, are they all, can you just buy any old passive sampler, or where do you get them, and how do you figure out what's good and bad?
Let me go all the way back to the top here for a moment. So there's different ones that are dependent on what you're sampling. You can self, they're very cheap, they're reusable. You can find a partner who will build them for you, sell them to you. You can go to a researcher. You know, for example, if you want to measure air, there's things like silicone sheets that you can buy online through, you know, various distributors, or radiellos who are sold by, some of these have, you know, manufacturers who will sell them to you. Like Radiello is a patented project for sampling the air. You know, the POSIS is something developed by USGS. They can help you with that. ChemCatcher is for water, just like the POSIS, sold by a company. I recommend making your own. Like I said, I don't make any money off this design. I didn't invent it. I can't patent it. I'd love to help you use it, but I don't make millions of dollars if you choose to use this tube. But you know, for those who are really interested, reach out to me and I can describe it. But you buy a tube, you fill it with sorbent that you bought from Oasis and Waters Corporation, and you put it in the water. It's really simple to extract. It's really easy, and I know there's a lot of private labs that are also willing to work with these. So I won't bore people with the details, but it's not hard.
Okay, well, so that goes on to another question, which is cost of these things, but also the analysis of them. And yeah, how do you know, what kind of method or who's doing the analysis and what's just, you know, compared to maybe a traditional grab sample,
Yeah.
you know, analysis or.
So a lot of the private labs I've spoken to are willing to do the analysis. It's very easy for them compared to a water extract. You can also always pair with research institutions, right? State agencies. I use these with state agencies and the EPA all the time on private research projects I work on outside of Tetra Tech. But, you know, you would basically, all you have to do to extract these is soak the thing in methanol, concentrate the methanol, and put it into your LCMS. So it's a little different than filtering liters of water through a solid phase extraction, where you need a big apparatus, you need a manifold, you need filtration, you know. It's a little easier. Doesn't take 8 hours of work. So I reach out to honestly, just reach out to private labs. I guarantee you most of them will say, yeah, I can soak that in methanol and do it for you.
Okay. How about how long do you leave the passive sampler in the environment to do a test? And what kind of parameters do you need to be measuring or knowing in order to?
That's a good question. So I recommend about 2 weeks. I didn't go into it here, but a lot of my research was on calibrating these things, figuring out how they work, right? Having some confidence. I recommend about 2 weeks. I've done 7 days, 2 weeks, a month, a year, but those are really for research purposes, not necessarily for applications, right? So I would say about 2 weeks, and then you don't really need to know too much outside of the water temperature that you're in. The nice thing about this design, if I go to this thing, because you've got this really thick membrane around it, they're very flow resistant. So they're going to work the same basically in every river. You don't need to measure the water flow of the river. They're going to work the same in every estuary for the most part. And you know, the details on how to calibrate for that I can provide later. But you know, it's very simple. It's going to work the same in almost every groundwater environment, essentially, because of that thick membrane versus things like these where there's really no protective membrane. It's just a sheet in the water, right? So that's very variable with flow. The POSIS is very dependent on accurately measuring the velocity of the water, whereas my studies were focused on showing that this doesn't really care. It's just fast or slow. That's all it really cares about.
Okay. Oh gosh, there's so many questions here. Have you seen PFAS, PFAS in a sea foam? Is it in the foam?
I've never measured a sea foam, but I'm very interested in sea foams because there's a lot of research recently that shows that they are significant sources of PFAS to the atmosphere. So I would think that yes, you would see it in sea foam because these are surfactants. They do collect at the surface microlayer. But I personally have not done that research, but I'd love to.
Okay. Do you do any data normalization prior to NMDS or PCA analysis, and maybe define those acronyms?
Sure, yeah. So principal component analysis is PCA. Yeah, you do need to use data normalization. I use an R script, which is an open source software that automatically takes your data and normalizes it for use in a PCA. You can always check if your data is normally distributed using, you know, statistical tools. You can do it in Excel, you can do it in R. But things like NMDS are really great for non-normal data, meaning that it's not normally distributed, which sometimes environmental data is not. So for NMDS, for PCA, yes, I pre-normalize everything. Basically, so you have like a composition instead of a raw concentration, or a percent contribution instead of a raw concentration. PCA doesn't work if you have 0 values, whereas NMDS does. So you also have to, for PCA, you typically have to like clear out any zeros or NAs, and that's why I was talking about replacing it with like some value. Like a method detection limit divided by square root of 2 is often used, but there are many others you can use as well.
Okay. We are right up against 3 here, but I'm going to ask one more question, and then if people can stay on a little longer, we can get back to Mike Eberle and some of his stuff too. If people want to keep putting questions in, if you can stay. So, you know, the results from passive samplers versus grab sampling, are they expected? I think you showed that they can be very different, but we pretty much use the grab samples in our regulatory and our legal matters, though. So is there a way to, how does this passive sampling fit, or how do you work that into your grab sample?
Yeah, that's the $1 million question that I will be tackling probably for the rest of my career, because not every environment is super dynamic, right? So some, like drinking water, might not be super dynamic, where a grab sample can capture a pretty good picture of what you've got. Maybe a lot of sites in the ocean aren't very dynamic. We found that the Arctic didn't seem to be all that dynamic. It seems like whatever PFAS we found 2 years ago, we still found there this year. So maybe you don't need a passive sampler for that, other than reducing the method detection limits. The issue is you've got to understand, you really have to be an environmental scientist and understand what you're sampling. Because if it's a dynamic system, then yeah, making your regulatory decisions off the grab sample is always going to have its limitations. You could be sampling at peak high, peak low, could be sampling right in the middle, you'll never know. So one of the things I really recommend is that, yes, make your permitting decisions off grab sampling, because that's what the EPA wants, that's what the state wants, that's all we do right now. One day they will develop a passive sampler method. I'm trying to work with them on that actively, and then maybe people will make their permitting decisions on passive samplers. So for now, use a passive sampler just to try it, see what you get, see how different it is, see if they're really cheap, do it once or twice, see what happens.
Okay. So here's a question from a regulator, actually. So the state gets a lot of requests regarding whether CycloPure can be used to monitor ambient surface water and/or private drinking water. Do you have any thoughts on these samplers in particular? Are there other ones that are commercially available that you think might be better for people to use, or?
Yeah, what a question. I used to work for CycloPure for a short internship. So I'm guessing that what they're referencing is the cups that they sell basically for sampling drinking water. Those haven't really been calibrated for use. They basically sell like a filter that you run under the water and then you mail it back to them. Those really haven't been calibrated for the environment. That wouldn't be all that different than a grab sample, because if you're just taking a scoop of water and pouring it down there, it may give you very accurate data, but it's not really all that different than a grab sample. It might cost you a little bit less to do, so that is good. But it's still just really a grab sample. I was in talks with them about developing their own line of passive samplers, so we'll see if that ever comes to fruition, but I do know their media and I do know it works for PFAS. It's got some limitations. It's really bad with the short chains relative to other sorbents, but it's still good overall. So that would be my answer.
Okay. This question, let's see, I'm just continuing on. It is after 3, so I do want to just acknowledge that if people do have to drop off, but I'm going to scroll back up and look at some of the other questions, or people can still type them in. This one could probably go for either one of you. What are the most significant precursors present in typical municipal wastewater? So significant meaning responsible for the degradation into terminal PFAS. Oops.
I could tackle that unless Mike wants to give it a shot.
Sure. It depends on the time. Right now, as I explained with an AFFF and over time, right now 6,2 is probably the most common telomere that's present in currently manufactured material. But you could have big slugs of 8,2 in the longer chain telomeres if you had input from a source that was older. Say they did a really major cleaning at a high school that had old carpet. You could have a big influence for a short time period of 8,2. And actually, we saw some of this during COVID when they cleaned, like they did some deep cleaning of high schools and schools that were closed down, where you saw some of the older telomeres show up.
Okay, so 6,2.
Yes, it's the most common now. Yes.
Yeah. Okay. And that's degrade. What's the terminal products that come from that?
Heptanoic, hexanoic, and pentanoic acids.
Yeah.
Okay.
PFCAs.
Okay, and yeah, somebody else had asked earlier back during Mike's presentation about 6.2 FTS and just let me see, where is it? Just, yeah, again, the sources, the typical source of that. Is there a typical source, or it's just really used in so many places that
It's used everywhere. It's what replaced PFAS and PFOA basically. So it's
Okay.
used in every material that used to contain the longer chain PFAS compounds. Well, not everyone, most of them.
Okay. Okay, so I did scroll back up, and I'm going to some of the questions that we didn't ask earlier. This is one with Mike and his grab sampler, his the grab sampling and the low flow sampling. What did you purge? Were the wells purged? They just weren't super developed, or what?
It was a combination of no development in some cases where it's high turbidity, and then the wells were purged with maybe just a limited volume or 3 volumeless, but there was no criteria for purging. In other words, purging to clear or low turbidity. It was just some 3 well volumes in sample. In most cases, in some cases, it was just a grab sample from a temporary well. But anytime you had the high turbidity, it was in areas where that water could have been developed to a clear groundwater sample.
Okay. Again, I think this is Mike. If you want to evaluate AFFF used for firefighting on a roadway accident or something, in the right of way, with the presence of PFHXA and PFHXA/PFOA be the analytical forensic indicator for that?
It would depend on when the foam was created that was used in the accident, basically. So if it's an older foam, it was it's been around since the 2000s. It would be PFAS. If it was a foam that was generated between 2000 and 2015, it would be 8.2 and 6.2 would be the primary components. If it was a current foam, a C6 foam, it would be hexane sulfonate. 6.2 would be the major component in the soil. So it depends on when the AFFF was manufactured.
Okay.
And then those car accidents and accidents along highways are tending to be a pretty substantial source for private wells in the area where the emergency response occurred.
Right. So going back to those micelles, which I still don't quite have my head wrapped around, because I'm not a chemist.
Well, they're bubbles. It's just really tiny bubbles.
So what concentrations do they form, and how do you know if that's happening or not?
And that's a great question, because in the text they'll talk about micelle concentrations, critical micelle concentrations. That's where micelles form on their own, being in like the 300 to 500 ppm range, which you rarely ever see in the environment. But what doesn't take into consideration is the concentration of surfactants, especially ones that are looking for air, right in the micro layer of water, where that concentration may be way above 500 in that narrow range between the water surface and the air. So there's no direct way to measure that concentration. You can see it from just high concentrations of PFAS in water samples. If you shake up that water sample, it's going to foam. And that's where you exceeded it.
Okay. This is more, I'm down now with Matt questions. Did you look at total organic fluorine, the top analysis, and those kind of analytical methods when you to also look at the forensic part of your work?
Yeah, so in the river study I showed, we did do EOF, total extractable organofluorine, and we found that there was not really very elevated fluorine. So we didn't think we were missing much of what we were looking at. There was not a huge amount, and we deduced anything we were missing was maybe those FTCA degradation products. In a separate study that's not out yet, knock on wood, we did do EOF and suspect screening, developing methods for passive sampling. So trying to share the method to apply to passive samplers to do suspect screening and EOF on passives to make them more useful. So stay tuned.
Okay. Here's a question that I'm actually wondering about. So 6.2 FTS and 8.2 FTS may not be the original precursors, correct? Or are they? And, you know, are they daughter products of something else? So is that correct or not?
The precursor, the initial precursors are not 6.2 FTS, and well, they can be a minor component of it, but it's their parent compounds that have functional groups tacked onto that base telomere, basically. 6.2 or 8.2 could be the base telomere, and then you have a functional group tacked onto it that gives that compound specific properties, or it is a patent compound for a specific company manufacturing it.
Okay. Let's see. Yeah, lots of people want the slides. Yes, we will be posting PDFs of the slides either later this week or next week, hopefully. Let's see. I'm not sure who this question's for. How do you feel about 24-hour flow proportional composite sampling in permitting, given the trade-off of better coverage versus possible analyte loss? Not sure who that's for.
I unfortunately have to bounce to another meeting, so I can
Yep.
take one more question, or I can just head out. I don't know if there's any more left.
Okay, I think we're mostly done now, and it is 10 past, so I think we will just end there. So thank you so much to both Matt and Mike for sharing so much information, and I hope everybody enjoys the rest of their day. So thank you so much. Thanks
Have a nice
again,
day.
Matt and Mike.
Bye, everyone.
Bye-bye.